Hello everybody, thank you for your interest in today's presentation. My name is Moritz Farm and I will talk you through our paper about occupant-oriented economic model predictive control for demand response in buildings. On the agenda we start with the introduction and I will explain to you our methods, evaluate it and finally come to a conclusion. In the introduction, we start from a centralized energy system where we want to include renewable energies, which results in a decentralized energy system where it's difficult to balance energy generation and demand. However, as buildings consume a major part of energy, they offer large potential for shifting energy. This energy is used by occupants in buildings as they require thermal comfort. So in summary, we have conflicting controls. On the one side, we want to shift energy with demand response. On the other side, occupants and buildings want to feel good, comfortable. Occupants interact with the building energy system, and occupant behavior in buildings involves the presence of occupants, adjustment of thermostats, operation of windows and shadings, and the use of appliances and lighting. To solve this conflicting control, we can use model predictive control as an established multi-criterion optimization, and as a novelty, we include occupant behavior into model predictive control, as we can see here on the right side. The upper part is occupant behavior, below is model predictive control. The occupant behavior can be separated into set point prediction and heat flow prediction, and in this present work we focus on set point prediction, and we include them into the cost function and constraints. Cost function weights between controllables, in our case demand response and occupants thermal satisfaction. The constraints define a range of permitted input and output variables. In our case, the desired temperature range and the permitted control input values, so the heating capacity. The optimization defines the optimal input trajectory over a future horizon, which considers constraints, cost function, also future system dynamics, which result from a building model, and the disturbances can be internal or external heat gains. As an essential part of the model predictive control design, we develop a thermal building model. We identify it from measurement data and validate it. The model is designed in a resistor-capacitor analogy, where the main input is the heating and the output the air temperature. As this is a linear system, we can represent it in state space notation, where x are the states, u input, z disturbances. The full list of control variables is shown here in the table, where we also have the states of interior, inside and outside wall temperature. The disturbances are the global solar radiation and the ambient air temperature. We also see here an electrical price signal that will be later used for the model predictive control. We use the state space model in the optimization in a time discrete formulation instead of time continuous as previously. We minimize the cost function L. The function L contains the standard temperature tracking term for the reference temperature and a term for minimizing energy costs, where we have the dynamic energy price signal multiplied by electricity used. Finally, we have a sub-constraint temperature term to limit the temperature in a certain range between 18 and 26 degrees. We also limit the input, but as a hard constraint, so that the electric power used always must be below 1500 watts. Now it's important to know how to include the attendance schedule into the cost function and constraints. Depending on the occupant's presence, the values of the weight coefficient lambda and the temperature constraints are scheduled. So whenever the building is unoccupied, we set the lambda value to 0. Then we can maximize demand response and minimize occupant's thermal satisfaction because no occupant is inside the building. And additionally, we decrease the penalty beta for the self-constrained temperature. For the results, we evaluate the general impact of the attendance schedule and we compare the PI controller with the model predictive control. Therefore, we have one controller that applies an attendance schedule and one that is constantly heating. So we can see that one controller meets the reference temperature of 21 degrees all the time. Therefore, the heating is on a relatively constant and low level compared to the scheduled PI controller that has higher peak loads but also may turn off during times when the building is unoccupied. In contrast, the model predictive controller can already predict when the building will be occupied and reheat in advance. Depending on the value of lambda, the focus of occupants' thermal satisfaction is defined. So higher values of lambda mean more focus on occupants' thermal satisfaction. But as we want to provide demand response and occupants' thermal satisfaction at the same time, especially the values between 0 and 1 are important for us. So, for example, this 0.5. What we also can see is that the heating is reacting on the price signal, that we are heating more when the price is low. Now we discuss the results with respect to the KPIs, the grid costs, and the occupants' thermal satisfaction. In general, the attendance schedule reduces grid costs for both the PI and the model predictive controller. For the PI controller, we have 17% less grid costs, and for the MPC, minus 10%. This comes from the lower heating demand during unoccupied periods. However, due to the transition phase between unoccupied and occupied periods, the mean average error increases, which results in a lower occupant thermal satisfaction. For the PI controller, we have plus 1.51 Kelvin MAE, for the MPC plus 0.42 Kelvin MAE. Based on these results, the model predictive controller significantly outperforms the PI controller. The grid costs are 40% lower, while the MAE is significantly lower with minus 0.97 Kelvin. So we have much higher occupants' thermal satisfaction. This comes because the MPC is less sensitive to the transition effect between the unoccupied and occupied period. The nature of the MPC is that it can account for future occupants' presence and already heat in advance. The optimized control input can respect predicted future system behavior based on the building model, also weather forecast, and demand response based on the dynamic energy price. Finally, we summarize how to consider occupants' thermal satisfaction and demand response in model predictive control, and discuss the benefits of occupant-oriented model predictive control compared to classical PI control. To consider occupants' thermal satisfaction and demand response in MPC, we use the occupancy schedule and dynamic energy prices. The schedule determines when the building is unoccupied and then sets the weight coefficient lambda to 0. Also, it decreases the penalty in the temperature constraint. So, when the building is unoccupied, we have maximum flexibility for the demand response. However, the model predictive controller requires a thermal building model and measurements of heating and temperatures. Therefore, the benefit of this controller is that the included schedule reduces the grid cost significantly because of the lower heating demand during unoccupied periods. And we also see that this model predictive controller outperforms the PI controller with 14% lower grid costs and 0.97 better occupants' thermal satisfaction. The high performance of the model predictive controller results from its optimal predictive nature, as it can account for future system dynamics, occupant behavior, weather forecasts, and energy prices for demand response. Thank you for your interest in this presentation today. In case of questions, I'm happy to answer them.